Coming to you from our studios in the Planck's Constant Building, located in the lovely Hilbert Space Plaza, it's the #1 show in the Quantum State, the Planet TV Show.
Welcome to the Planet TV Show. I'm Lucian, and we are on the net. Yes, today is Friday, 9th of June. Spin for the day is counterclockwise. Soon it will be a full moon. Not yet, though, for all you lunatics. Oh, don't forget. Because it's better to hurt your mouth than someone else's nose. You know that, though. Still need your vote. Vote, 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 vote. All right, let's get straight into it tonight, shall we? Yes, we shall. All right. It is not often that I am prompted to use this time or space for an editorial, but this is one of those times. I recently received an email from a viewer who expressed concern over the reality of global climate change and the perceived political nature of my comments on the subject. This editorial is a response. First, I'd like to say that I have not seen the movie by Al Gore. I have not followed or read the popular opinion makers' take on this subject. I do not care what the politics of this subject are. This is an issue of scientific fact and theory. It is not an issue of politics, and therefore any political aspect of this subject is irrelevant to me or my analysis. I am a scientist, and what I know about this particular subject is a result of the job I do. I'm a strategic analyst for a group whose job is to gather, examine, analyze, and synthesize huge sets of facts and data into a predictive pattern. And then I am asked to predict what will be occurring at some point in the future. I use monstrous computational power along with massive databases and an almost carte blanche access to just about anything that is wired to the net. Here is what I know to be true. Global climate change is occurring. This is a fact that is not in dispute. Overall temperatures are in a rising phase according to every record-keeping data set that we have. NASA storm data from satellites show that storms are increasing in number and intensity. Temperature is rising and storms are increasing. By definition, climate on the Earth is changing. There are only two areas of disagreement. First, is this a climate fluctuation, meaning temporary, or a climate shift, meaning permanent, at least in human terms? And second, is this a natural set of events, or did we have something to do with it? And if we had something to do with it, did we just exacerbate an existing problem, or did we alone cause it to happen? None of these specific issues are agreed upon. The most likely situation is that the extreme positions, it is a completely natural phenomenon, or that we alone caused it to happen, are incorrect. Climate change is happening. It probably is not a completely natural change, and it is more than likely that we had something to do with it. From a strategic analysis perspective, if we had something to do with it, then it is not relevant how much we may be contributing or whether we alone are responsible. I'll explain that in a moment. What the analysis shows is that any contribution made to the global climate change by us is critical. So the only real question, from a tactical view, is whether there is anything we can do to stop affecting it. I have heard the position that it is arrogant for us to believe that we could affect the global weather. The general premise of that argument is that the Earth is so large that we cannot really have an effect on the planet or the atmosphere as a whole. This same argument was used in the issue of ozone depletion. Opponents of the plan to reduce ozone-depleting chemicals from use said that the damage to the ozone layer had to be due to some other source. Their position was that the amount of chemicals released into the atmosphere could not possibly be enough to affect the ozone layer. They also suggested that any restriction on the ozone-depleting chemicals would have a negligible effect on the ozone layer. But the reality has turned out much different in more ways than one. By strongly curtailing the release of ozone-depleting emissions, the ozone layer has actually healed up in places faster than was anticipated. This is good news for the ozone layer, but it brings up a few very important questions that are requisite in our understanding of the issue on global climate change. First, if the problem was so big, how could it have been corrected so quickly in certain instances? Second, would the atmosphere have corrected itself whether we reduce the ozone-depleting emissions or not? And finally, could this mean that the ozone-depleting emissions were not as destructive to the ozone layer as was previously believed? These are all good questions, and they're questions that we did not have the answers to until after we restricted ozone-depleting emissions and measured the response of the ozone layer. The answers have to do with the way very, very, very large systems behave during times of transition. Let me explain. In the past 20 years or so, mathematicians have developed a new form of mathematical analysis and computation called fractal geometric complexity math, also referred to as chaos dynamics. This system of math was developed as we began to attempt to do calculations that involve enormous quantities of individual components or pieces, ultra-large sets. Using massive computer power, scientists created models of real-life phenomena such as weather, chemical, astronomical, and atomic systems that had previously been beyond the capability of human calculation. And this is what they discovered. When a system is composed of many, many, many individual pieces at a level and scale beyond comprehension in normal life, then the system begins to show unique and unpredicted behavior called emergent properties. When that system undergoes expansion, increasing the number of the individual components, then these emergent behaviors very slowly increase until a critical point is reached. At that critical point, the system will either squelch down and stabilize at a lower activity level, or the system will undergo rapid and radical system expansion and growth corresponding with a massive increase and intensity of activity. This new level of violent activity and growth will maintain as long as the energy and individual pieces are supplied to feed the growth. Once either element is limited, the system will stabilize. If the overall system is large enough, then this phenomenon can be represented in multiple areas of the system, like storms occurring in different places all over the earth at the same time. If the overall energy and rate of the expansion in certain emergent behaviors is great enough, then either the new emergent activity will be sustained indefinitely, like the ice storm on Jupiter, or the stabilized point, where it stops changing, will be significantly different than the starting point. This is best explained by an example. Anyone who has studied chemistry is familiar with the idea of a buffered solution. In simplistic terms, a buffered solution is a liquid that has a reacting chemical in it, as well as another chemical, which is the buffer. When a third chemical that is reactive to the first main chemical in the solution is added, then the buffer prevents the reaction between the two ingredients from occurring. Even as more of the chemicals are mixed, the buffer prevents the chemicals from reacting. As long as the buffer is working, there is very little, if any, change in the solution. In a typical buffered reaction, the reagent, the second chemical, is continually added and the buffer prevents a reaction until a critical point is reached. At this point, the chemical reaction between the main chemical and the reagent occurs. The reaction occurs rapidly and completely. The reaction completely consumes all of one of the two ingredients and then stops. What does this mean for global climate change? It means that there is no way to tell a normal fluctuation from the beginning of a catastrophic shift until it is too late. The beginning trends in both a temporary fluctuation and a major shift are expanding, but only moderately. The difference in a fluctuation that stops and reverses is that one of the elements, either energy or the individual pieces, stops increasing in time. If neither of these stops in time, then there will come a point where the next small increase will be the straw that broke the camel's back, and a catastrophic shift will begin. This critical transition point shifting is fact. It is supported by the most advanced math we know, and this math accurately models every known example of large system dynamics that we have ever examined with it. The math cannot tell us when a catastrophic shift will occur in any large system, such as global climate, but it tells us that it will definitely happen once that critical transition point is reached. Which brings up the issue of strategy. Maybe man-made ozone-depleting emissions were not to blame for the destruction of the ozone layer, but their elimination was just enough to start the reversal process and allow the Earth to begin healing the holes that had opened up in the ozone layer. It is one of the unique characteristics of large complexity systems that small changes in critical properties that occur at transition stages can have huge impacts on the overall system. So even if our contribution to global climate change is small, it is strategically imperative that we stop. The closer we are to the critical transition, the more important every small addition becomes. But the reality is that our contribution is not really all that small. Since the Industrial Revolution, by any calculation, man has released trillions and trillions of tons of CO2 into the atmosphere. This is CO2 that was removed by the Earth millions of years ago, when the atmosphere on the Earth was much denser in CO2. A ton of CO2 is 2,000 pounds of carbon dioxide, which is a gas. The number of molecules of CO2 gas in just 1 liter is a multiple of Avogadro's number, which has 23 digits in it. This means that the number of individual molecules of CO2, carbon dioxide, that has been released by the burning of fossil fuels is mind-numbingly enormous. Each and every molecule of CO2 is an individual piece in the complexity system we call the atmosphere. Everything we have learned from complexity math theory says that when you increase the individual components in any ultra-large system, that system will undergo change. When you massively increase the numbers of elements in a system, then that system will undergo radical and permanent change before stabilizing. Radical, long-term change in the atmosphere is called climate change. CO2 levels are rising, and the atmosphere and climate are changing. There is almost certainly a direct correlation between them. But even if our contribution of CO2 is not the main reason for climate change, it is still important that we reduce and eventually eliminate the release of CO2 from fossil fuels. If we are close to the tipping point, then any small amount of increase may be the amount that pushes us over the edge. By the same token, if we are close to the tipping point, then any small decrease will take us that much further from the edge of a catastrophic shift in climate. And according to the math, we cannot know for certain how close we are to the point of no return until it is too late. So if you're looking for absolute proof, you will not get it unless you are willing to sacrifice everything. Because you cannot have absolute confirmation that a catastrophic change is occurring until it has begun and cannot be stopped. Most importantly, the question of whether the current climate change is temporary or permanent is most likely a question of how big the current climate change that we are undergoing turns out to be. If efforts to reduce known climate-altering emissions are successful in reducing the trend to global warming, then it is likely that the climate change will fluctuate rather than shift. Global weather is a massive chemical reaction that obeys the rules of complexity math. By removing both energy and constituent elements from any chemical reaction or complex system, the activity level of the system will stabilize. Reducing human emissions of CO2 will remove both energy and constituent elements in the overall atmosphere. This is not a hypothesis. Throughout the geologic history of this planet, when atmospheric levels of CO2 were reduced, the Earth's weather cooled and calmed. Right now, the Earth's weather is warming and getting more active. This is a fact. The climate is changing. As for whether the climate change is temporary or long-term, there is no way to tell unless we try to reverse any effect we may have had on the climate, just like with the ozone. So the critical issue of reversing climate change is really a question of us doing the only thing that we have any control over, and that is reducing the CO2 emissions from fossil fuels. This ancient source of CO2 is contributing to global climate change, and it is CO2 that does not belong in our modern atmosphere. And it is an astronomical amount that we have released and continue to release. Finally, I've also heard the position put forth that the earth is much older than we are, and it will be here long after we're gone. This position is often put forth by people who don't believe that the climate is actually changing, or who don't believe that we have had any effect on the climate. Their position is that many people have predicted the end of the earth from one disaster or another. All of them have been wrong, as the earth is still here and accounted for. This is actually true, but it misses the point of the discussion. Global warming does not pose a threat to the earth, nor does it pose a threat to life on this planet. Both the earth and life on the planet will survive the effects of global warming and catastrophic climate change. What is in danger is us. Even a small, temporary climate change in the geologic time frame and terms, which is what weather is measured in, could be another ice age that lasts for 10,000 years. Thanks for watching the show. I'll see you on the next time. In the meantime, have yourself a good whatever. And if you want to call and leave a message regarding this show, please do. And don't forget to vote.
I don't know, you think a princess and a guy like me?
No.